We should be ready to go. Okay, it's a great pleasure to have Bryan Clark visiting us virtually from Chicago, Champaign. I will leave Luke give a more detailed introduction. Do you want to say a few words, Luke?
Oh yeah. Thank you very much for coming here, Bryan Clark, to give a seminar. He works on various things. He has a very impressive CV, in my opinion, actually. But today he will talk about entanglement transitions. But he also works on Monte Carlo and neural network states, many things in computational physics, actually. So thank you very much, Bryan, for coming here. Please, start when you're ready.
Great, thanks. Thanks everyone, and thanks Luke, and thanks for inviting me. I'm happy to come virtually and share this work with you. By all means, please interrupt and ask questions as I go along. Then that will be good. So today, what I'll be talking to you about are entanglement phase transitions, and I'll tell you what those are in more detail in a minute. But for those of you who are sort of familiar with many-body localization, that's an example, or random transitions in sort of quantum circuits or quantum tensor networks, that is also an example, and we'll get into that in a little bit more detail in a moment. And my focus really will be work we've done sort of generically trying to use numerical techniques to really learn properties of these entanglement phase transitions. And so what I'll say in a little bit more detail in a moment is that while the entanglement phases are now being relatively well understood, our understanding of the phase transitions are still very poor. And part of that reason is it's actually very hard even to answer very basic and simple questions about them. And so there's a lot of sort of phenomenological theory, but very little sort of concrete knowledge. So before I get started, let me just point out my collaborators, my current and former students and postdocs. They're really the ones who have done the work that I'm going to talk about today. So this is Sanjay, a former student of mine. This is Benjamin Villalonga, a just recently former student of mine who's now at Google Quantum. This is Ryan Levy, who is my current student and has done all the work on the random tensor networks that I'll tell you about. And then some of this work is with David Luiz, who is also a former postdoc of mine. So let's go ahead and get started. So today what I'm going to talk about is this sort of broad umbrella category of entanglement phases. And so an entanglement phases is it's a phase of matter, but it's a qualitatively different sort of phase of matter than, say, a quantum phase or a thermal phase. So in a quantum phase or a thermal phase, what you should look at is, for example, you should look at the ground state, and there should be some discontinuity in the ground state or in the energy, or something like this. In a thermal phase, we're used to having discontinuities in the partition function. In an entanglement phase, the thing that is changing on us is the entanglement. So we tune some coupling constant. In this case is often going to be disorder. And the entanglement of some quantum state is going to change. So for example, in the case of many-body localization, what we'll do is we'll tune some coupling constant, and the many-body localized phase will go from a phase where the relevant quantum state is volume law to the relevant quantum state is an area law state. And the relevant quantum state here is very different from what we're used to in the many-body localized phase. Instead of the thermal state or the ground state, the relevant state here is a high-lying excited state, the 2 to the 31st excited state or something, any excited state that's at finite energy density. And so that is what an entanglement phase is. And there are really very few sort of known examples at the moment, and I'll be talking about 2 of them. One is this many-body localized phase. This is certainly the most important, popular, and relevant example. And then there's sort of a new kid on the block. There's a new phase, which is these random quantum circuits or these random tensor networks. So here, the relevant quantum state is no longer an eigenstate. There's no Hamiltonian. We explicitly define a state. We define a circuit in a particular way. We tune some property of that circuit. And again, we'll have a change in the entanglement from area law to volume law. Okay, so the first, say, 2/3 of my talk will be on many-body localization. And then the last third of my talk, I'll go ahead and I will talk about random tensor networks. Okay, so let me go ahead and get started. So I'm sure many of you have heard about many-body localization. Let me just kind of step back and give you sort of a broad overview. Many-body localization is this new qualitative type of phase of matter, this umbrellaed entanglement phase. And the canonical sort of standard model of MBL, you have a one-dimensional spin chain. You have a Heisenberg term, and then you add some on-site disorder. And so almost all many-body localization is interaction plus disorder. And in this case, the disorder, we have a on-site magnetic field. These H's are chosen randomly between -1 and 1. And the coupling constant, the thing that we're going to tune, is this W, which is the strength of the disorder. Let me ask, can you see my mouse as I'm sort of pointing at things?
Yes, yes, we can, yes.
Okay, great. And so we will go ahead and we will tune the disorder, and that will move us around in this many-body localized phase. So as we crank up the disorder to something large, we end up having ourselves out here, and we're in the many-body localized phase. In fact, this has a special name, the fully many-body localized phase. And the fully many-body localized phase has various properties, sort of the two canonical ones. I've already told you the eigenstates have area law entanglement, so that's weird. If you just took a typical Hamiltonian, a typical eigenstate, you would expect them to have volume law entanglement. And that just follows from the fact that such a eigenstate needs to look thermal. If I'm at high energy density, I'm typically at a finite temperature. And if it looks thermal, all thermal density matrices are volume law. So it also follows that a typical eigenstate should be volume law. These eigenstates are weird, they're area law. That means they have sort of a notion of locality, they have a notion of distance, hence the name many-body localization. Because they're area law entangled, that means they can't look like the thermal density matrix, and that means thermalization breaks down. So we're used to having our cup of coffee on the table and it equilibrating to the room. Here, this is sort of the quantum equivalent, right? You have a large quantum system. The small subsystem should equilibrate to the temperature of the entire system. And yet, in the fully many-body localized phase, that fails to happen. And it fails to happen largely because excitations are local, entanglement is area law, and so we can't move around the energy. And then what we have is as we tune down W, as we come down in W, we end up going into the ergodic phase here. Actually, things are a little bit more subtle. The phase diagram here consists of both the disorder and the energy density. The energy density is a sort of a moral equivalent of temperature, but temperature makes no sense because thermalization has broken down. At least it makes no sense in the many-body localized phase. So instead of temperature, we say, oh, that's 50% up in the spectrum. And so over here, we have a mobility edge. If you're very high in the spectrum, you're still in MBL. If you're in the middle of the spectrum, you're ergodic. Okay, and the fully many-body localized phase is reasonably well understood now. There's sort of a phenomenology, kind of a theory behind it. And there are sort of three sort of equivalent legs of that theory. And so I won't talk a lot about the phase today, but I'm going to spend a couple of minutes just overviewing this. And then what we'll do is we'll worry not about the phase, but the phase transition. So one sort of canonical way of thinking about the many-body localized phase is to think in the context of L-bits. So L-bits are Hermitian operators. They're these tau i's. And it is a true statement that any Hamiltonian I give you, I can define n Hermitian operators that commute with each other, that commute with the Hamiltonian, and that are orthogonal. And the special thing about the many-body localized phase is these Hermitian operators are local. So they have not quite compact support, but compact support plus exponential tails. They commute with the Hamiltonian, and much of the sort of low entanglement, thermalization, et cetera, can be understood in this context. And so this formalism was developed by sort of David Hughes and Dmitry Abinin and company. And many of us have worked on sort of pulling out these L-bits and understanding them, et cetera. There's an equivalent formulation that we've sort of worked on that I like, which is the following. If I give you a many-body localized Hamiltonian, you can go and you can ask, what is the cost of diagonalizing this many-body localized Hamiltonian? And you can characterize that in various ways. So one way you can characterize it is you say, look, I want some unitary circuit that diagonalizes it. How deep is that unitary circuit? And what you can show by some combination of numerics and analytic argument is that the quantum circuit that diagonalizes a many-body localized Hamiltonian is short. It's of small depth. The sort of moral equivalent of that in the tensor network language, which is another way to say this, is that you can write a matrix product operator for diagonalizing the many-body localized Hamiltonian. That matrix product operator has small bond dimension. So we worked on this. There's work from Anusha, Chandra, and company also on this. And then there's, and this implies the L-bit formulation. The L-bit formulation implies this. There's one final sort of way of viewing this is that the eigenstates of the many-body localized phase are actually extremely simple. And they're extremely simple in this very sort of formal way. What you can do is you can define a set of ground state tensors. These are essentially matrices or three tensors, and a set of excited state tensors. And then you say, look, I would like to generate one of the eigenstates. What I do is I choose for each site either a ground state tensor or an excited state tensor. This generates sort of a combinatorial set of tensors. There's 2 to the n of them. There are 2 to the n excited states, and this generates the whole spectrum of excited states. Each of these tensors is sort of fixed for all system sizes. Okay, so this is sort of some phenomenology of the MBL phase. The MBL phase is primarily a one-dimensional state of matter, although we've recently been involved in some work looking at more than one dimension. Let me just mention it quickly. So one of the sort of standing questions about the MBL phase is to ask, can you get MBL in 2 and 3 dimensions? And this is a hard sort of mathematical question that we don't really want to touch. So even in 1 dimension, it's been hard to prove. There's this nice proof by Embry that shows that MBL exists in 1 dimension. So let's not worry about that formal question. Let's just ask ourselves the question, as a practical, pragmatic matter, do you see something that looks an awful lot like MBL localization in 2 and 3 dimensions? And so what we did is we developed a new algorithm that finds these L bits in 2 or 3 dimensions, sort of a adaptive selective CI for many-body localization. And we apply this algorithm to the 2D Heisenberg model, to the 3D Heisenberg model. And this is a graph that's showing you disorder versus sort of extent of the L bit. Is it compact or not? And what we see is we see that at small disorder, it's fairly extended. And at large disorder, it jumps and becomes extremely compact. And so we don't want to sort of touch the rigorous mathematical question, but just sort of the pragmatic question, does sort of MBL-like phenomena exist in 2 to 3 dimensions, at least in these particular models? We have good evidence that it does.
I mean, did you run those simulations for a reasonably long time? Or because my understanding is that it has been it's more or less a consensus has emerged that MBL doesn't exist in higher dimensions if you wait long enough.
So that's a good question. So so let me answer that in 2 parts. The simulation is not doing dynamics. The simulation is building up sort of approximate L bits. And it is run for a long time to build up these approximate L bits. Now, it is true that there is this sort of consensus and story that in 2 or 3 dimensions, some sort of avalanche behavior will eventually destroy the MBL phase. And I would not say that the numerics dispute that because there is a sense in which that's sort of a mathematically rigorous statement. That's really a statement that in the thermodynamic limit, the formal MBL-like phase shouldn't exist. And I suspect that's true, although I have no personal sort of stake either way. All we can say is we can say that as a pragmatic matter, there are L bits that commute at sort of their commutators at kind of the 10 to the minus 3, 10 to the minus 4 level with, and they're local, they're very compact with the Hamiltonian. And so because it's 10 to the minus 4 and not 0, this doesn't prove that there is an MBL phase. But what it suggests is that there is going to be sort of a set of time scales and a set of length scales where in the real world, you ought to be able to see this kind of phenomena. So this is why I want to sort of be careful about what I want to say. I don't want to say anything mathematical. It is almost certainly true that some sort of avalanche behavior formally destroy it. But the fact that you can get L bits that commute extremely, extremely well strongly suggests that some non-trivial amount of the phenomenology at finite timescales and finite length scales should survive.
So could I also ask, so you're not doing this on finite systems. These things are, you're constructing them, it's not like you're trying diagonalize, right? You're getting operators which nearly commute or essentially commute.
So we are getting operators that nearly commute. And for all intents and purposes, we're doing them on infinite systems.
That's what I thought, yeah.
We treat the system as extremely large, and because the operator is compact, we just build it out and out and out. So you can think of this in infinite systems, but the operators only approximately commute. And so formally, that doesn't tell you anything from a rigorous point of view. MBL, you need honest to goodness zero commutator. This just tells you that there's something that looks very, very close to an L bit on these systems.
So for certain timescales, it might be quite accurate then, right?
That's right. But you wouldn't expect it necessarily to be accurate for the thermodynamic limit for infinite.
No.
That's right. And so all we can say is a practical matter, there is sort of a time scale at which you ought to be able to see MBL-like behavior. Great. Good questions. Any other questions? Okay, so what I'd like to talk about then for the rest of the MBL section here is I would like to focus not on the MBL phase proper, which I think as a community, we've really gotten a pretty good handle on and are, have good theory, really starting to understand, know a lot of the properties numerically and can understand them analytically. I'd really like to start talking about the transition. So by that, I mean, as we tune W, we reach this place where we're sitting right between the ergodic and MBL phase. And I'd like to try to begin understanding some basic things about that transition. Okay, so we can ask what is known about that transition. So to begin with, there's a huge amount of renormalization group theories, phenomenological RG. In fact, there are more RG theories than there are practitioners in the field working on RG theories. So multiple people have multiple different theories about how to think about the MBL transition. And this is great, right? I mean, RG is a practical and useful tool to understand how phase transitions work. But at some point, what these really boil down to is phenomenology. You come up with some RG-esque rules, you apply the rules, you write down some flow equations, and you get things. And so we want to take sort of an alternative tack here. We want to just ask sort of very basic questions that we can start chipping away at and probing using numerical tools. So we are not aiming at a full-fledged theory here. We're aiming at beginning to answer basic questions, because even ideas like, can we think of eigenstate phase transitions in kind of the context of first and second order phase transitions, things like that are still kind of poorly known and poorly understood. And so there's a sense in which, despite there being a lot of work at the transition, this is still a very open field. So we'll tackle in the MBL phase three particular concrete questions. To begin with, what we'd like to do is we'd like to ask sort of the question, what is the entanglement at the transition? The entanglement of the eigenstates has been sort of the key defining feature of MBL. In the MBL phase, it's area law. In the ergodic phases, it's volume law. And so you can ask what's going on at the transition. Is it still area law? Is it volume law? Is it volume law, but not the ergodic volume law? Volume law means it's linear with system size. Maybe it's a half or a quarter or something. Is it logarithmically entangled? This is something that we don't know. And or at least didn't know before some of our work. And it's sort of a question we'd like to tackle, we'd like to answer. So that's the first thing I'll tell you about. The second thing I'll tell you about is to say the following. What does sort of a typical correlation look like at the transition? If you tune yourself to the transition and you look at some correlation function, we'll look at the quantum mutual information, but almost certainly all correlation functions are the same. And you can ask, look, is it algebraically decaying? This is kind of what our intuitions suggest for sort of a standard quantum phase transition, right? You tune to the gapless point, you should see some algebraically decaying correlations. Does it decay exponentially? Is it some stretched exponential? There are lots of options. And there's no sort of solid theory that definitively tells us what's going on. And the final MBL question I'll address is not about the typical correlations, but really about the correlation length, both at the transition and as we approach it from the MBL side, and how that relates to sort of the breakdown of non-locality.
Excuse me, in your SL, what does the subscript A stand for there?
Great. So this is the entanglement as a function of subsystem size. So L sub A is the size of the A subsystem.
Okay. Thanks.
So this will be sort of the MBL end of the talk before I get to the random tensor networks. So let's go ahead and start with the first question. The first question is, what is the entanglement as a function of subsystem size? So we look at a subsystem size 1, 2, 3, 4, etc. The entanglement will grow, and really the question is, how will it grow? And there were sort of various different thoughts on this, and those thoughts gave different answers, actually. So there's a beautiful argument by Tarun Grover that I'll introduce in a moment. That says, look, on very generic grounds, really it has to be volume law at the transition. Not only does it have to be volume law, but it has to be sort of the ergodic volume law. So at the infinite temperature point, at midway in the spectrum, the volume law for many body localized phase of the ergodic, no, I'm sorry, the volume law for the ergodic phase is a slope of log 2. And Tarun says, look, there's almost no other option but that. There is a scaling collapse done by lots of people, but probably best done by David Luiz and company. And their scaling collapse suggests that the transition should be localized. But we know that the scaling collapse is untrustworthy. We know that the scaling collapse is untrustworthy because it gives us some critical exponents, and those critical exponents are rigorously mathematically forbidden. And so the scaling collapse looks good, it looks reasonable, but is known to be rigorously impossible. And then, so I'll then introduce sort of what we can say and sort of how we can tackle it using a numerical approach. Okay, so here's sort of the outline of Tarun's argument. Tarun says, look, in the volume law phase, we know what must happen. This is just finite temperature, thermodynamics. We've known this forever. As we increase the subsystem size, if we look at the entanglement for various subsystem sizes, it has to be a straight line, and that straight line has to have a slope of log 2. This is what we mean by volume law. We mean as the system gets bigger, or as the subsystem gets bigger, the slope goes linearly with the subsystem size. Okay. And what happens in the MBL side? Well, let's not talk about what happens here for the moment, but certainly at large LA, it's area law. What does area law mean? Well, it means the slope is 0. It means the subsystem size gets bigger and bigger, but we don't gain any more entanglement. Okay, and Tarun says, look, there's nothing else reasonable that can happen. And I may not be doing full justice to Tarun's argument, but he says, there's going to be some correlation length in the system. If you're smaller than the correlation length, if your subsystem size is smaller than the correlation length, then this part of the entanglement must be volume law. There's just no choice. It doesn't know that it's an area law phase yet. And so here it must be that this is log 2. And then you get bigger than the correlation length and it keels over and it becomes slope 0. Okay, that sounds very reasonable. It's almost certainly what must happen. And then what must happen is that as we tune disorder, you end up going further and further, looking like your volume law, because the correlation lengths should get bigger and bigger. And then at some point, what should happen is that you should diverge from this volume law entangled subsystem, and you should eventually become area law. And so as we're going up in this graph, you're going to more and more closer and closer to the transition, lower disorder. And exactly at the critical point, well, maybe your correlation length goes to infinity, and then you're sort of volume law the entire way. Your volume law is log 2. It's the same volume law that you should get in the ergodic phase. Clearly, this must be what's going on. And this is really a nice argument. He argued there's a part of this argument where you use strong subadditivity to argue that this curve has to be monotonic in this way. And it's sort of a very reasonable thing on general grounds. In fact, the paper is called Certain General Constraints on the MPL Transition. Okay, great. So the upshot of this is really the transition, the entanglement of the transition must be volume law. Okay, but as I said, there's a counter to this, and that is people have done scaling collapse and gives wrong critical exponents, but nonetheless, the scaling collapse suggests that it should be area law. So our goal really is to go in and—
Sorry, when you say that it gives wrong critical exponents, what does that mean?
There's a critical exponent nu associated with the scaling collapse. And in disordered systems, there's a generic argument by Chase and company that has to be greater than 2. And
sorry, just to go back, there's an exponent nu associated with the scaling collapse. You said, is this nu is usually the symbol that's used for the correlation exponent with temperature. So is that the same? Is it a correlation exponent? That's,
I mean, it's a dynamical scaling exponent.
It's a dynamical
scaling exponent, and it's essentially in disordered systems. There's sort of generic physics arguments that it has to be a certain value. Here, actually, there's a more rigorous statement that can be made. There's very sort of careful mathematical arguments by Chase and company that people like Anusha Chandra and company have really looked at carefully and sort of validated that it applies here. And when you do the scaling collapse, you just don't get an exponent that's large enough, is really what happens. Now, the scaling collapses are hard, right? This is numerics on 20-site systems, so it's not super surprising that this fails. But it just means that you shouldn't completely trust everything that's going on with the scaling collapse because you know it's not formally getting everything right.
Right. And why don't you expect a critical exponent for the volume, instead something between volume and area law? I might expect that there was a critical exponent.
Yeah, so that's not a crazy expectation. I guess what I would say is once you do the scaling collapse, you have a scaling function. You can actually read off the entanglement, and it appears to be that entanglement at the transition is localized. And so there's nothing really deep here. That's just what you end up seeing. There's no deep reason it could not have been something else. In fact, we'll see in a minute, sort of from numerics, it looks like something else. Great. Any other questions at the moment or further discussion on this? Okay, so what we would really like to do is we would like to go in and we would like to take every eigenstate. We'd like to compute sort of these slopes for every eigenstate. And our anticipation is that sort of they should either be 0 or log 2. And from that, we should peel out the entanglement. And the only problem with that is that naively doing this is sort of a disaster. So what should you do? Here's your subsystem, length 1, length 2, length 3, length 4. You can compute the entanglement on all these cuts, and you're going to get a curve that looks sort of jaggedy, right? I mean, it's a disordered system. There's no translational invariance. Everything is ugly. And so this is your curve, and you're trying to ask your question, well, what is the slope here? Is it 0? Is it log 2? Okay, this is obviously kind of a nonsensical question. So then you go and you say, oh, this is silly. That's one eigenstate. Just go ahead and do an average over all eigenstates, over all disorder realizations, et cetera, you'll get a smooth curve, read off whether the entanglement is 0 or log 2 or something in between. Okay, and you can do that. So here's some data up to 22 sites. And this is disorder W versus the slope at, say, L/4. And you can stare at this and you can ask, okay, it goes from something close to log 2, that's the volume law phase, to something close to 0. And now you just want to answer the question, you want to answer the question, what is the slope at the transition? So this is some finite size system. I mean, who knows where the transition is? There's some broad transition region. What we'd like to be able to do is point at the transition and say, the slope is 0.5 there, or the transition is here is log 2. But this obviously can't be done, right? At the very least, what you would need is you would need some sense for this finite size system where the transition is. But better, you would really want to sort of look at this very carefully and try to understand what's going on with the entanglement. Okay, so really what we need to sort of pull this off, and this is sort of the sort of technical trick that allowed us to really make progress on this problem, is you need to be in a situation for each and every individual eigenstate. You can really look at this S of LA curve and stare at it and sort of get its slope and whatever. Okay, and so to do this, what we did is we developed sort of a argument that there's a way to turn these kind of curves for a given eigenstate into curves that are nice and beautiful and for which have a well-defined slope. And so the trick here is one can use some arguments about subadditivity of entanglement to show the following. I take an eigenstate, and I would typically do subsystems of size 1, 2, 3, 4, et cetera. If instead you do a window averaging, you do all subsystems of size 1, call that S of 1, to all subsystems of size 2, call that S of 2, to all subsystems of size 3 and 4. What you can do is you can rigorously prove, actually, that you get a curve that is now convex, a curve that has to look like this. And so this window averaging, it seems like sort of kind of almost a silly technical trick, actually really gives you a lot of leverage, a lot of power here, because what it does is it now gives you, for each individual eigenstate, a curve from which you can read off the slope. And so this is just a cartoon here, but over here we have real numerical data. So each of these lines, these jagged color lines, is the data that we get if we do a particular subsystem of size 1, 2, 3, 4. And then if you do the window averaging for this particular eigenstate, you get the solid yellow curve. And so it turns something disastrous into something usable. And now what we can do is we can go ask our question. So here what we have done is we've just taken one Hamiltonian and we have looked at, a series of Hamiltonians where we tune W, all of the same disorder pattern. And we have looked at various eigenstates for that Hamiltonian. And these are single eigenstates. There's no averaging going on other than this window averaging. And we've just plotted them here. And if we believe Tarun's argument, what we should expect is that each of these curves should look the same at small L sub A, at small L. And then at large L sub A, they should start to diverge. Right? They'll look volume law for a while, and then they'll kill off. And that's not at all what any of this looks like. It looks like here, these are some representative set of curves. The curves don't intersect at all. If I start with sort of different initial slopes, then I have different slopes at larger L sub A. And so something is not right about sort of this general argument. And so what we would like to do now is try to step back, look at distributions, and extract what's going on. Okay, so the first thing we can do, this is sort of a poor man's approach, but we can say, look, given that we have not only the average over the slopes, but each and every individual slope, we can look at different moments of that distribution. And one thing we can look at is the standard deviation. And something we have as a community have learned about many body localization is that almost always sort of the finite size transition is where the standard deviation is maximal. And so if you just look at the standard deviation of these slopes, it has a maximal peak here. So we could tell ourselves, this is roughly where the transition should be. We can go up and we can look at what the average of the slope is. And we see that the average of the slope appears neither to be 0 nor log 2, but log 2 over 2. Okay, we'll just think a little bit more refined in a second, but that's like a poor man's guess if you were to force to sort of just look at this data. So this wasn't on sort of anyone's plate. No one said, you know what, the entanglement at the transition should be exactly half of the entanglement. Okay, so this confuses us for a bit. So what's going on? Well, instead of just looking at moments of the distribution, we should just go back and look at the distribution. And what we see is the following. This is the distribution at different values of W. Here I have them labeled as H. And at the ergodic phase, the slope is all sort of at log 2. The MBL phase, the slope is all at 0. But at the transition region, what you see is you see something that's actually bimodal. So if you sit right at the transition, essentially exactly half of your states have slope 0, exactly half of your eigenstates have slope log 2. This is actually where the log 2/2 is coming from. It's not that all of your states are somehow kind of weird volume law. It's actually that you get a bimodal transition. This should really sort of strike you as kind of first order-esque, although we'll see later that there are second order-esque aspects of the MBL transition. But this particular thing really feels first order. Your area law right up to the transition, you hit the transition and your eigenstates bifurcate. Half of them are volume law, the ergodic volume law. Half of them are area law with slope 0. And then as you walk over the transition, everybody jumps to volume law. There's sort of a discontinuous jump in the entanglement over the transition. And you might say, look, this is a disordered average problem. You know, this is probably coming in because some of the disordered samples are in one place and some are the other. So we went back and we looked at particular single individual samples. So this here is an example of an individual sample. This is again the slopes. For one sample, we pull all the eigenstates. A bunch of them are at 0. A bunch of them are close to log 2, even for an individual sample. This is not a very prototypical sample. This particular sample is a little bit cherry-picked because to get good data, you have to sort of search for one where the bimodality is obvious. But nonetheless, even in individual samples, we find sort of a clear bimodality of the states. And so this is sort of an example where sort of doing a bunch of eigenstates, really sort of characterizing what's going on with the slope and things, you really can sort of tackle these problems in a way that is hard to do sort of analytically.
Sorry.
Yes.
The transition looks closer to being second order to me, but just from the bimodality is not very pronounced, and if you went to a larger system, it could possibly be. I mean, you have fluctuations that are crossing the button from one to the other. It looks like the other one in your preview. Go to the previous slide. All of your curves look like they cross around HC.
Yeah. So
which
many
would be
of them. Sorry,
which would suggest that there's some L independence associated with the crossing point, and one might expect that that was the critical point, and that it is capturing something about the L equals infinity limit, and that's often the case when you do finite size scaling.
That's a great intuition. That's exactly right, actually. So it's really dangerous to call MBL either first order or second order. And the reason it's dangerous is actually there are second order aspects, as you've pointed out here, sort of this crossing that's telegraphing the critical point. And there are also first order aspects. There's no deep reason that this sort of first order and second order sort of concepts that work for thermal and quantum phase transitions have to directly translate over to MBL. And in fact, we'll see later that there are other aspects that look a lot second order like. But this first point you make, so you say, look, actually, like, this is not great bimodality, right? Great bimodality will be like fully at 0 and fully at log 2. And you're right. And this is an artifact of the fact that we can only do tiny system sizes. So if I'm a little bit more careful here, so this is 12, 14, 16, 18, 20, 22. As we crank up the system size, it becomes more and more bimodal. So at the 18 site, that's that yellow here. It's a little hard to see. There's a little hint of bimodality, but it's very kind of flat. As we go to 20, it becomes more bimodal. As we come to 22, it becomes much more extreme. And so it is our expectation, although this is numerics, right? Anything can happen, but every indication is that as the system size gets larger, the bimodality gets stronger. And I'm not showing it here, but actually what we've looked at is we have graphs that look at the variance of this distribution. So a unimodal distribution has some limit in the variance. The bimodal distribution has a particular variance. And what we see is as we crank up the system size, that variance is monotonically increasing in a way that would be reasonable to anticipate that it's going to reach sort of the maximal bimodality at infinite system size. So that is our expectation. That is sort of now the general consensus among the community. Of course, it's numerics, it's tiny system sizes. This is the best we can do. This is kind of really state of the art here. The problem is you need the full spectrum, or at least many eigenstates sort of smack in the middle of the spectrum. Every indication is as we get to bigger system sizes, it becomes more bimodal. Probably it will be sort of arbitrarily bimodal at L.
Your susceptibility argument doesn't quite support that, I would say.
So tell me what that is.
Your susceptibility, you showed a susceptibility, the standard deviation. It wasn't growing as I would have expected for a first order. I would expect that first order type transitions would have a very large type of, that the peak would grow with the system size more or less linearly.
Yeah, so that is fair, and that is why one, right, should be careful about sort of taking general sort of expectations from first order, but it certainly is growing. So this is 12, 14, 16, 18.
That's
20.
the type of thing that I would expect from a second order. I would expect a rounding and a shift of the exponent, and it looks like it's the peak is getting sharper. It's moving closer to HC, and that's the rounding and shift that's often associated with finite size scaling again.
Yeah, so I agree. A lot of this is going to be second order, and we'll see in a little bit more evidence of second order like behavior. So I don't want to call this first order, but if you just want to ask the empirical question, what is going on with the entanglement? Maybe I should be careful and not call this first order, but it really, the best numerics that we can do at the moment really suggests that this entanglement will continue becoming more and more bimodal. And that is sort of I don't want to like say that this is first order. I think I should have been more careful there because a lot of the correlation lengths and various things look second order like, and we'll see that more. But it is true that the entanglement becomes more and more bimodal. And this is just what the numerics is showing. And I don't think there's any good theory, even thinking about second order phenomena, where we would expect to see sort of a greater bimodality that somehow gets cut off at some point at some system size.
Okay, thank you very much.
Yeah, thank you. Thanks for the questions. Are there any other questions about this? I'm going to move on to sort of my.
Yeah, I have a general question. I mean, so when you say you have this HC or your critical one, this is you have different HCs depending upon your energy density, I suppose.
Yeah, that's right. And so
does the phenomenology all match? I mean, you know, naively you might hope that everything looked the same within reason.
Yeah, so that's a good question. So yes, you do. This is all at the 50% energy density, which is the temperature. And this is the only place we did this particular study. So these are very expensive. They use a lot of supercomputing time. We would expect that if we went down to 30%, you would see a similar phenomenology, but we don't have numerics to back that up. We've been able to do this study at sort of one energy density, right around 50%. And at that energy density, we see this. We would expect it to exist at all the energy densities where the transition happens. But for this particular study, there is no numerics to validate that.
And would they be more expensive to do let's say 30% energy density?
I mean, not more expensive than this study, but equally expensive. So this burned however many hundreds of thousands of supercomputing hours, and so then to do sort of another all over again could it be done? Yes. Did we decide it was sort of important for?
But you expect it to be the same.
I'm sorry?
You expect it to be the same.
Yeah, we expect it to be the same, but I that's just an expectation. I don't have any data to back that up.
I guess there would be exponentially many states at the center of the spectrum anyway, right? So it would represent sort of high temperature generically, like just taking 50% because of the density of states.
The density of states is maximal there. That is sort of the infinite temperature point. But we have done other studies where we've looked at other places in the spectrum. I mean, there are 2 to the 20 states here, right? So there are more than enough states to get a bunch of states of the 30% of the spectrum. But as I said, it's just It's expensive, and we didn't feel it was worth it for this particular analysis. Great, thanks. Other questions about this part? Okay, so I'm going to go on and ask my second question. What do the typical correlations look like at the transition? And I sort of telegraph some answers. Maybe they decay algebraically, maybe they decay exponentially. That would be sort of more what you might expect for first order. The thing that would be sort of maybe most anticipated is maybe it's going to be a stretched exponential with an exponent and a half. Where did I pull that from? Well, so Daniel Fisher and company has sort of the seminal paper on the infinite disorder fixed point on random singlet phases. And if you look at a random singlet phase, if you look at the infinite disorder fixed point, that is what is expected of the correlations, that the correlation should have sort of the typical correlation should be a stretched exponential with exponent and a half. So e to the minus r to the half. Okay, so what correlations are we going to look at? Well, we'll look at quantum mutual information. That's sort of a bound on all correlations, and it's a sort of a correlate kind of ambivalent to the type of correlation. So here, the quantum mutual information will be between 2 sites, site A and site B. So this is the definition of quantum mutual information: entanglement of A plus entanglement of B minus the entanglement of AB. So this was first looked at in many-body localization by Thomas C., Baradis, and Pullman. And we're going to sort of build on that work and really try to answer the question, what does it look like at the transition? Just to sort of tell you a little bit about quantum mutual information, the largest quantum mutual information you can have is 2 log 2, although that's weird because you have to essentially have a maximal singlet between two sites to get it. So the largest practical quantum mutual information I have, if you're entangled with more than 2 sites, is essentially log 2. And so here, we're not going to look at the quantum mutual information primarily. We're going to look at the log of the quantum mutual information. That's really because this is a disordered average problem. When you do disordered average, there are all sorts of Griffith effect-like things. And so rare instances sort of confound the averages. And so to be careful, what you do is you look at sort of the log of these things so that rare large instances don't screw up all your averages. Okay, and here we did a study with really like a gazillion eigenstates. So this burned a good fraction of my supercomputing time for the year. And this is like the summary of all of this work. And then we will like stare at this and figure out what this tells us about the typical correlations. And the reason that this took so much is you just need a huge number of instances because many of the things that you're looking at are a little bit rare. Okay, so this is a histogram of various disorder realizations. And this is a histogram of the log of the QMI as a function of the range. So this is a single particular instance. The quantum mutual information between sites 0 and 2 are relatively large. The quantum mutual information between, say, sites 0 and 9 are there, but like tinier. And so this is like the data. We're taking these snapshots, reading off their values, histogramming them. Okay. We see in the ergodic phase at W of 1, the quantum mutual information is some value, it's some nice Gaussian, the log QMI is largely independent of range, has no range dependence. That'll become important later, in particular what we mean when we say those words. In the ergodic, in the MBL phase, this purple here, the quantum mutual information is doing 2 things. One, it's decaying quickly. This is log QMI. And in addition to decaying quickly, it is spreading out. It's becoming more spread out. And the green region is the transition region, and that's the region that we'll care about in particular. Okay, and so now what we're going to do is our goal is to look at this log QMI And mainly what we're going to look at is like just how fast this is decaying. And that will tell us about the typical QMI, the typical correlation. So the right way, again, this is just a trick of log averaging. The right way to define a typical correlations is the exponential of the average of the log. So that's what everyone means when they say this is the decay of the typical correlations. And so again, this is numerics, so this is the best we can do. But what we see is we see that at the transition, at W of 3, we can look and we see that the log QMI, the rate at which these histograms, the average of those histograms decay, that rate decays linearly. Very, very cleanly linearly on a log scale. The X scale is log R. And so typically, for those of you who are sort of used to fitting log scales like that, it's very rare that you get something that fits beautifully all the way down to really R of 1. It's 10 to the 0. And it fits here with a slope of a half, in this case 0.54, although if you tune it a little more, you'll get a half. And so what this tells us is this tells us that the average of log QMI goes as minus beta R with beta of a half. So the typical quantum mutual information is e to the minus r to the half, some coefficient, right? E to the minus a, r to the half, e to the minus a square root of r. Okay, so this is an honest to goodness stretched exponential. So there's sort of a couple steps here because we are looking at things in log scale, but this is an honest to goodness stretched exponential that is happening at the transition. As you go deeper into the MBL phase, it is still the case that at large R, you get something that looks linear, although it doesn't, it's not sort of invariant in the sense that at small r, it falls off. That's okay. Really, all you care about is the large R behavior, although sort of the data is not as good, but this is still linear. It's still a stretched exponential. The exponent here, this is W of 8. This is deepish in the MBL phase. The exponent has changed. It's no longer 0.54. It's 0.98.
Sorry to, I'm confused by how did it become beta to the power of R from a linear, from proportional to R?
So what's going on here is that we are looking at this on a semi-log plot on the x-axis.
Oh, so what you meant, the line above here should be beta log of R.
The line above here.
You have beta equals 1/2, and you have the exponent. The average of the log of QMI is proportional to minus beta. It should be log of R.
Right.
Okay, all right, sorry.
So this gives this typical quantum mutual information. Sorry about that. And so we see that at the transition, we have e to the minus root of R. We see here we have e to the minus r, sort of a decaying exponential. And so in the ergodic phase, we see just garbage, right? So this doesn't fit a line at all. There's no polynomial here. It's not particularly surprising, but large R, this is just not nothing polynomial. Okay, so what we can do is we can now go and we can take this exponent beta from each of these individual W's and we can graph it. So this is what we've done for L of 14 and 16 and 18. We've gone to every W. We've pulled the exponent beta from the stretched exponential, and we can look at what it gives you. So to begin with, this is W. This is this exponent beta. Over here, we've plotted data, but this data is garbage. That's why it's lightened out. The fits here are just crummy. So it's not surprising in the ergodic phase, there's nothing to fit. There's no line at large R, it does some curvy thing. And so where the fits are very good, we pull them out, we make them solid. And what we see is we see deep in the MBL phase, it becomes just a plain old boring exponential decay, e to the minus r. As we approach the transition, we eventually get to the point where we hit the transition. And at that point, we get exactly e to the minus some coefficient times root r. Okay. And this happens very cleanly in the following sense. We get to the exponent of a half, And then exactly past the exponent of half, the goodness of the fit essentially becomes 0. So that's what this is now, sort of a technical point. But as we come down in disorder, we reach some disorder where the fit is good. So this is some average residual of the fit. The fit is good exactly where the exponent is a half, and the fit then becomes sort of infinitely bad. So this is really telling you that right down to the transition is an honest to goodness stretched exponential fit. And the transition is the cleanest data we have in the sense that, all of the MBL data, it fits at large R, but not at small r, but exactly at the transition, it really covers this line beta r exactly, beta log r exactly. Okay, so this is what's going on. We find exactly a stretched exponential here. This is something people have looked at for a while because of this sort of infinite disorder fixed point. This is another technical slide. It's not particularly important to understand this, but let me just say it. This is the coefficient a. So this is e to the minus a, r to the beta. So as a gets bigger, the system localizes. So that's good. Over here, a is getting bigger. We're getting deeper in the MBL phase. The system is localized. That's what we expect. Here, a is getting smaller. The system must be delocalizing with respect to a. The only way to sort of compensate is for there to be a beta here, a stretched exponential. So this picture is sort of an independent verification that this part of the phase diagram, there must be something going on with the stretched exponential. Again, this is technical, not super important. The key takeaway is that we find a stretched exponential in the full MBL phase, but one that ends at the transition as e to the minus root r. So we can go back and we can say, look, is this evidence that we have a random singlet phase, the infinite disorder fixed point? That's not what was expected. But maybe, I mean, this is exactly the correlations that Daniel Fisher and company have found for that. And so we can now look at the other moments of this distribution. So this distribution is the distribution of log QMI. And there's actually a prediction for this, for all of the moments of the infinite disorder fixed point. In the infinite disorder fixed point, the moments should largely all be range independent outside the mean. So the mean goes as e to the minus root r, and all of the other moments of this should have no dependence on range. And so we can look at these. So let's say we take the third moment, the skewness. We sort of zoom into the transition, and what we see is that the third moment has a crossing point here, and at the transition, independent of the range, these different curves are range 1, 2, 3, 4, 5, whatever. This is a function of w. Right at the transition, they all have the same skewness. Okay. We can do the same thing for the fourth moment. I think it's the kurtosis. We have a bunch of lines of different range. We zoom in, we look at the transition, and they all cross essentially at a single point. Okay, so that looks very promising. That's true as expected for the infinite disorder fixed point, except for the second moment. So we go look at the variance or the standard deviation, and there is no crossing as a function of the range. And so that is the only thing that falls apart. This is very much like the infinite disorder fixed point as far as the correlations go. You have e to the minus root r decay of the typical correlations. You have every moment above 3 to be range independent. But the standard deviations are different. There's a range dependence of the standard deviations. And so it's like tantalizingly close, but not exactly the same thing. So that is sort of the answer to the question, or at least the best answer that we can get from sort of state-of-the-art numerics. What do the correlation functions look like exactly as you hit the transition? The typical correlations. We've done this funny log averaging. Okay, so that's that part of the story that I wanted to tell. Are there questions about that?
And Bryan, the transition points there, they look to be a little bit lower than what you were getting before.
Yeah, so that's a great observation. So right here, you can look at where these all cross and these all cross, and you say, look, they're not all exactly at the same point. They're not all exactly where we got before. And so I can pull up the graph, but let me just tell you what happens. What we looked at is we said, okay, can we look at how these move with system size? And what we see is we see that they're all moving in such a way that is consistent with them all coming together at the same place. Now it's tiny numerics. We can't sort of promise that that is what happens. But what we really have in terms of the data is we have a point where essentially all the ranges, except for range 1 here, actually, it's at a very, very close point. We have a system size dependence that's all drifting toward essentially the same thing. And again, the best we can do at the moment is say that certainly looks like everything is coming together to be range independent. And this is actually, so if you go back to say David Luiz's paper and you look at all the finite size transitions of the different things he measures, entanglement and fluctuations and this and that, they all also have very different, not very different, but like non-trivially different transitions. And then as you crank up the systems, they all sort of drift together. So this is not surprising. You expect that the different observables for a finite size transition will give slightly different things, and that your expectation is that in their thermodynamic limit, everybody comes together.
Okay.
Thanks. Any other questions?
Yeah, so is this at all related to what people like, I think Vasseur and maybe Hughes and other people are saying about this connection with the KT transition, Koster-Thales?
Yeah, so that's a great question. So they have this sort of theory that there's sort of a critical phase because there's sort of this whole line of KT transitions as we go from the MBL to ergodic. And so, right, we've all talked together and we've all sort of discussed this. And the upshot is really that this is probably related because you have this line of stretched exponentials, but there's no sort of clean relation. Their theories at the moment don't explicitly predict this quantity. And so there's no obvious sort of concrete thing you can point at and say, this explicitly tells you about the KT transition. But because you get sort of this line of stretched exponentials, I think that there is a relationship, but I can't point to something and say, well, their theory predicts particularly this behavior.
They're not looking at that observable?
They are not computing that observable explicitly in the RG. That's right.
Yeah, okay.
But they're sort of, right, they're aware of this work. And so people are sort of thinking along the lines of how to go back and really sort of get some of these quantities. So at the moment, I told you there's a lot of RG and we've been doing a lot of numerics as have other people. And there's still a little bit of a disconnect between some of the numerical things that are known at the transition and what the RGs can compute. And I think as time goes on, that will slowly sort of come together. But at the moment, it's hard for us to sort of compute some of the things the RG looks at, and it's hard for the RG to compute some of the things that are sort of tractable to attack numerically. Great, other questions about this? Okay, so the final MBL story I want to tell you is about the correlation length of the transition and sort of what that telegraphs about the breakdown of non-locality. So the game we're going to play here is we're going to tune disorder. So this is a numerical experiment, right? We're going to tune disorder from a large to a small disorder. So we're going to write down a Hamiltonian. It's going to have the same disorder pattern of the magnetic fields. And then we have some W and it will be large and we'll slowly cool it down, slowly turn it to small. And while that happens, we're just going to watch all the eigenstates. And what's going to happen to the eigenstates? Well, as they tune W, they're going to collide, right? And they're going to collide and they're going to hybridize into each other. And so we're just going to watch sort of thousands of eigenstates collide and hybridize sort of all the way down. This is not looking at the low-lying eigenstates. This is looking at the whole spectrum. Okay. And our concern, we will care about two things. We'll care about the strength of these collisions, and we'll care about the range of the collisions. So here is sort of a zoomed out view of, it's not even that zoomed out, but we're going from 4.6 to 4.45 in W. We're coming down in disorder. And these are different eigenstates. And you can see, for example, this blue and red, it's zoomed in. They run into each other and collide. What do you mean by collide? Well, there's some avoided level crossing here because it's a finite size system. And when they collide at any given point here, we can work out sort of the strength of the collision. What do I mean by that? Well, we can write the red eigenstate at W plus dW in terms of the red eigenstate at W plus the hybridization with everybody else. We only move that red eigenstate a little bit. It only moves sort of dW amount. And so what we should do is we should say, oh, it hybridized by dW times 23 of the blue state plus 1/10 of the green state plus 100th of the orange state. And that's the strength. The strength of the hybridization between red and green was 1/10. So that'll be sort of our metric of strength. So here at this particular point where they collide, there's the red gets hybridized with a lot of blue, less green, less orange, less yellow. This is a log scale. And strength won't play an important part in the part of the story that I'll tell you. We're always just going to look at some fixed strength. So we'll consider strength of 1/10 or strength of order 10 or something. We'll just fix strength and all of the rest of the part of this talk. And the other thing that we can ask about when eigenstates collide is we can ask about what is the range of their collision. So what do I mean by those words? Well, roughly what I mean by those words is that every eigenstate has some L bits associated with it. That L bits are essentially some up, down, or eigenvalues, 1, 1, -1, 1. And what we'll do is we'll look at the L bits where two states differ. So here are the L bits for the red eigenstate. And here are the L bits for the yellow eigenstate. They have Hamming distance of 2. They differ in 2 L bits, but their range is 3. The farthest L bits that differ, this one is up here and down here, and this one is down here and up here. The farthest L bits they differ are range 3. Let me say that in a slightly different way. We know that there's
Can't hear you, Bryan. I think you're muted.
sorry about that. I moved around my the little bar and it muted me. Okay, so let me say that in a slightly different way. We know there's some unitary that diagonalizes the Hamiltonian. That's a short quantum circuit in the MBL phase. There are actually many such unitaries because they differ by permutations of rows and columns. They differ by the signs. These all give unitaries that diagonalize the Hamiltonian. We want to choose the one that corresponds to the lowest depth quantum circuit, lowest bond dimension MPO. And heuristically, we find that the Wagner-Wilson flow achieves this. It's not a regular statement, just we want to find sort of a short, a small depth unitary, Wagner-Wilson flow will generate it. And so what does the unitary do? Well, it takes an eigenstate and produces a product state. It's sort of the definition of what the diagonalizing unitary does. And this product state gives the L bits. So if you just want to ask like the pragmatic question, how do we get the L bits? We run the Wagner-Wilson flow to generate the diagonalizing unitary. We take the unitary and we multiply it by the eigenstate. That gives us some product state, and those are the L bits. From the L bits, when eigenstate EI and EJ collide, we have product states I and J that are the L bits that are colliding. They differ by range 3. Okay, so that's the game. And now what we're going to do.
Just one question.
Absolutely.
When you're diagonalizing this, how is the range determined? Because the original Hamiltonian you had, it's how far the it's lattice spacing apart, whereas when you've used the unitary, it's mixed. So what is the meaning afterwards?
Great, it is mixed. So the way you should think about this is that in the MBL phase, although it's mixed because it's being done largely by a short quantum circuit, it hasn't mixed too much. So local L bits turn into what are essentially local excitations. And so what this unitary does is it unmixes it in a way that sort of breaks locality as little as possible. So it doesn't drag a local excitation over here to a different L bit over here. This is another way to say what this particular choice of unitary does. And this is really important for this analysis. We really need to get ourselves on some definition of kind of the underlying L bits, the underlying sort of local excitations. And this, throughout a series of papers, we've really been able to sort of argue that this is a very reasonable heuristic way.
So there is some small error on in whether it's the red one or plus or minus 1 in this. Is that what it means?
I mean, I would say that the mapping could have been different, for example, in the sense that, say, these two spins could have exchanged, and that still itself would have been reasonably local. So I would just not so much say it's an error, say that there are a related set of unitaries that all give essentially the same mapping or very similar mappings. And then there is another set of unitaries that are just disastrously bad. So if I had an excitation over to the left of my system and it flipped the spin over to the right of the system, that would be a very deep unitary because it would have to drag that information all the way across the system. And so we want to avoid that kind of things. And heuristically, the Wagner-Wilson flow never does that. It always maps sort of local things to local things.
So just to make sure I understand, are you doing this in the localized phase now, or?
We are doing it through the localized phase out to the transition. We are also doing it in the ergodic phase, although we're not using that data very heavily. So you might say, look, in the ergodic phase, does this make a lot of sense? And I can wave my hands and I can say, look, even the ergodic phase, if this algorithmic procedure does a good job of keeping things as local as possible, that's still what we want. As local as possible is still very non-local in the ergodic phase. But it's still sort of a consistent thing that is mapping uniquely eigenstates to L bits. But we won't worry about the data in the ergodic phase. Let's just worry about the MBL phase as it approaches and touches the transition.
So you're getting close to the LBL phase.
We're definitely
getting
close to
the transition. Sorry, yeah.
Yeah, because we're hitting the transition. And in fact,
Yeah.
I'm going to argue something based on this at the transition.
Yeah. Okay. Good.
Okay. Other questions about sort of the setup here? So I should say, I know I'm going long, and I was warned I can go long, but at some point when I overcome my welcome, you should just tell me and I will stop talking. Okay, and so what I'd like to tell you is sort of a tale of two probabilities. So when these two eigenstates, when any two eigenstates collide, these are related probabilities, we can look at the probability that this pair of eigenstates hybridizes over sort of any range R cluster. There are lots of range R clusters, so we're going to say, look, what's the probability to hybridize over any of them? And then the related thing is C, which is the probability that this colliding pair of eigenstates hybridizes over this specific range R cluster, maybe these particular 3 sites that are apart. Okay. And they're related, like there are 2 to the R range R clusters. So C is P over 2 to the R. It's just combinatorics. Okay. And so in the MBL phase, everything decays exponentially. Clusters are all local. So the probability that you differ when you collide by any range R cluster is just some e to the minus alpha R. I'll show numerics that validate this in a minute. In the ergodic phase, there's no notion of distance. All clusters are equally likely. 2 eigenstates collide in the ergodic phase. And the probability that you hybridize over any range R cluster is actually exponential in the range, just by combinatorics. There are lots of range 20 clusters, and so it's just likely that you're going to collide over one of those clusters. Okay. The probability you collide over any specific cluster is constant. It's range independent. All clusters are just equally likely in the ergodic phase. There's nothing special about any of them. Okay. And then we can just step back and ask, like, what's the only possible reasonable answer for the thing to happen at the transition where locality must disappear? You're at the transition. What should be the probability that you pair of eigenstates hybridize over any range R cluster? And there's only like 2 reasonable answers to this. Either P's got to be 1 or C's got to be 1. One of these things have to be range independent. Either it's got to look just like the ergodic phase, which would be weird, but not impossible, or it's got to be that somehow the probability to hybridize over any range R cluster is 1. We've lost all notion of locality, and that that's what's going on. Okay, and we can look at the numerics. And in fact, this is what happens. In the MBL phase, everything decays exponentially. The probability of hybridizing over any range R cluster, if the range is large, you're not going to hybridize over it. All right, that's reasonable. So this is of different strengths. I said we're going to fix strength. So pick one of these lines. As the range gets bigger, this is on a log scale. This probability decays exponentially. In the ergodic phase, although you don't have to trust this because we're doing this thing, although everything seems extremely trustworthy here, it grows exponentially. And in fact, these dotted lines are the combinatorial answer if all of the clusters are equally likely. And in the transition, it's perfectly flat. Essentially, the transition region exactly cancels out the combinatorial factors. Okay. This is what you might have guessed, right? If someone tells you these things and you had to come up, you would have said, ah, P was 1, and in fact, P is 1. P is range independent. Okay, there's something really cool that comes out of this. So if you have this probability C, you can go to find a correlation length, right? You have some probability here. You can write it as e to the minus r over chi, or z. Right? Okay, and you can define a correlation length from C. It's some decaying thing with range. And then you can just ask, what is the correlation length of the transition? Okay, and you just stare at that for a minute and you say, okay, we decided that P had to be 1. So C has to be 1 over 2 to the r. That's just the combinatorial factor. So we can just read off, like with 2 lines of algebra, the correlation length is 1 over log 2. Okay, this is nice. There are much more sophisticated arguments from DeRoque and company that you should get a correlation length of 1 over log 2 at the transition. But this is a very beautiful, sort of largely theory ambivalent way. Hasn't actually relied on any of the numerics, really. All we said is we made an assumption that, like, when 2 clusters collide, when 2 eigenstates collide, the probability that they hybridize over any range R cluster is constant. And under that assumption, you get this as the correlation length of the transition. And now you can go back to the numerics. And now you can ask, look, as we come from the MBL side, how do we approach this 1 over log 2? So the RG mainly makes it look like you should approach this 1 over a log 2 as some sort of square root. But this is not what we get. We can answer the question sort of, how does the correlation length sort of, well, it doesn't diverge, right? It hits 1 over log 2, but diverge, approach the 1 over log 2. And so what we do is we look at the alpha. This is the e to the minus alpha r. We plot it in various ways. We stare at it in various ways. And what we find is on the MBL side at large W, this is on a scale that's a log x, we find that it goes as log W over WC. 2 lines of algebra, if you ask, what does that make the correlation length? Well, what that means is that the correlation length goes as log W over WC plus log 1/2. So you ask, how from the MBL side does the correlation length grow? It appears to grow as log W over WC. Numerics is very clean here. These are all very clean fits to a log curve. That's what seems to go on. Something that was really surprising to us and interesting is we went and we said, oh, there are various correlation lengths in the literature, including things we've worked on. And do any of them match this particular growth of the correlation length? And so we pulled a correlation length that we did many years ago. This is some mean field approach. It's not really important how we get it, but we treat it as a fermionic model. We work out the sort of natural orbitals. Given the natural orbitals, we can pull out a correlation length. The nice thing about this is you can do sort of big system sizes and get a correlation length. The correlation length we pull out from this approach are these black dots. The correlation length we predict from this log W over WC plus log 1/2 is this black line. and they fit each other beautifully. This was like magic. We have no idea why this should be as good as it does. Everything just sort of falls together here. So I'm really proud of this work. I think I really like this result. It really gives us sort of this idea that what's going on in the transition, the way that locality is sort of switching to non-locality, is there's this special point that's not like the ergodic phase. It's really a point where there's a competition between the combinatorial factors of many, many range R clusters, and sort of just becoming non-local enough that you say, given this extra combinatorics, all range R clusters are equally likely. That gives this 1 over log 2, it gives this log W over WC, it matches other correlation links.
So where does this earlier work of yours appear?
Great, so I should have put in the citation here and I did not. It is, let me in a minute pull it up and I will, it's a PRB by Benjamin Villalonga, myself and Sean J.U. It's, I can stick it in the chat in a minute, but
Fine.
That should probably be sufficient to find it. As I said, it's a PRB with Villalonga, myself, and you as the authors.
So can you repeat a little bit where you got that curve from again? It went too fast for me.
Sorry. So the curve is coming from the following. So we have determined that the correlation length is log W over WC plus log a half. And here, what we're doing is essentially we have to pick the WC. That's like that's a fitting parameter of this. But once we pick the WC, that just generates this curve. Then we go and we pull out these old correlation links that were computed in a completely different way. No Wagner-Wilson flows, no nothing. There's some mean field-esque sort of way of getting these correlation links. And these are the black dots. And they just match up really, really well.
And that mean field-esque, that was the part I was interested in.
Okay, great. I can tell you that in a little bit more detail. Although it's, right, it'll take a minute, but let me tell you. So what we did is the following. We have developed, had developed a while ago, a way to get eigenstates for the MBL system using some DMRG-esque thing. You can't apply DMRG because it doesn't work in the middle of the spectrum. We developed something that lets us get eigenstates for 32 sites, 100 sites, etc., as long as you're in the MBL phase. So what we did is we went in the MBL phase and we get eigenstates, let's say 64 sites or something. And what we did is the following. In that paper, we were thinking of this Heisenberg model as a fermionic model. There's a Jordan-Wigner transformation that converts it back and forth. And from that fermionic model, what we did is we computed the natural orbitals. So the natural orbitals are the one particle density matrix, the eigenstates of the one particle density matrix. And given the eigenstates of the one particle density matrix, they're single particle orbitals, you can just measure the rate at which they decay. So we just fit those eigenstates of the single particle density matrix of this fermionic model. And given that decay, you can just pull out a correlation length. Okay, so they decay at some exponential rate, you just read off a correlation length. So that's how we generate it. So I call it mean field-esque because what we're doing is we're looking at an interacting Hamiltonian, an eigenstate of an interacting Hamiltonian, the 2 to the 31st eigenstate. And then we are pulling out the natural orbitals. The natural orbitals would be the right L bits if this was a non-interacting model, if this was like an Anderson model. It's not, it's an interacting model, but still we can just go through this procedure. We can pull out the natural orbitals, we can pretend that those are like L bits, we can look at how quickly they decay. So this is completely unrelated, like it's nothing at all like we did here. Here we took a Hamiltonian, we diagonalized it. The fact that these match is just, I mean, it's sort of too good to be true. And I don't have a deep understanding for like, other than they're both sort of probing really the honest correlation length.
Okay, thank you.
Yep, no problem. And so I should say this log W over WC, there really isn't any theory that gives this. So as far as I know, none of the RGs have that the correlation length as you approach in this direction should go logarithmically with W over WC. Great, so are there other questions about this? Okay, so those are my 3 stories about MBL. I also have some words I'm happy to say about random tensor networks, which is sort of another eigenstate model, but it is over time, it really depends whether people are interested in hearing either this whole thing or just sort of a couple summary words about this or not at all. And any of that I'm happy with.
Perhaps a couple of summary words would be sufficient, and it can guide questions afterwards.
Great, so let me just,
if you want to do it.
Right, good, so let me do that. So the game here is the following. This is also an entanglement phase transition, but it's not MBL, there's no Hamiltonian. You have a tensor network, you have a PEPS, it looks like this or like this. And what you want to ask is you fill up these PEPS, these tensors with random numbers, and you want to ask as you increase the bond dimension, the size of the matrices in this PEPS, do you get a phase transition from a PEPS that has area law entanglement to a PEPS that has volume law entanglement? And so there's a prediction by Roman Vassar and Andrew Potter and Andreas Ludwig and company that you do, excuse me. But to show that, what they did is they took this random tensor network, they mapped it to a StatMech model, they applied some sophisticated replica symmetry breaking, they crossed their fingers and hoped that the replica limit worked, and they said, oh, there's a transition somewhere. Okay, and so what we did is we said, look, let's just go do some solid numerics and figure out. And so when your bond dimension is 1, you have a product state, it's definitely area law. At large bond dimension, you should expect to have a volume law. So this transition is kind of expected. So this is, let me just kind of skip around here a bit. So really the upshot is that at bond dimension 3 and 4 and 5 and 6, you get something that is linear with system size. So we're looking at a PEPS that's L by infinity. As you make L larger and larger, the entanglement grows linearly with system size. And at bond dimension 2, it very, very cleanly grows logarithmically. So this is on a linear scale, everything is linear. Bond dimension 2, it grows extremely cleanly logarithmically. So somewhere between sort of 1 and 3, around 2, we expect a transition. What we did is we worked sort of then at fractional bond dimensions. What do we mean by that? Well, okay, you can have a 2.3 bond dimension, but some bonds can be 2 and some can be 3 and some can be 1. So that sort of the appropriate average is 1.4. And then what we did is we've done sort of a lot of sophisticated analysis to try to ask the question, where is the transition? And so I'm happy to detail all of this analysis, but what we end up finding, we look at the entanglement as a function of system size, just like we did in MBL. We look at the various histograms and distributions of the entanglement, because each of these PEPs is a random disorder PEPs. And we look at variances, we look at skews of that distribution, and all of this sort of telegraphs the same thing. What we see is we see that there's sort of a log critical point, or possibly a full logarithmic phase in the sort of region around 2. Below 1.9 is clearly area law. Above 2.2, it is clearly linear. We also do some sort of poor man's scaling collapse. So we go and we look at the tripartite mutual information. Mike Mulligan and David Hughes had done a study on quantum circuits that argued that this was not very sensitive to finite size effects. We see a crossing in the tripartite mutual information around D of 2. So all of that sort of, in summary, gives sort of validation to sort of this replica symmetry breaking analysis of Raman and company, with now a particular sense for where the transition is, and some hints of a possible intermediate phase, which would be particularly interesting, but is not really compelling enough to say with any certainty. There's certainly logarithmic critical point. Whether that extends to a full critical phase is still an interesting open question. So that's sort of the high level picture for what I was going to tell you there. I'm happy to take questions about that or any of the MBL stuff, or just kind of chat in general. Thanks for your patience and for listening and all your questions. And I'm happy to chat more.
Great, thank you very much. We kind of silent clappers. Some people can make noise, but it's a rather silent format. But thank you for an excellent talk and stimulating discussion on that. And we're open to questions. Please.
I have a general question about MBL
Yes,
in
John.
general. It's not really directly connected to your talk, which was
Okay.
which was very nice. But I mean, I've been following the story now for a few years. I mean, since I was in Trieste, basically, and there's plenty of people around there that work on these things. And of course, then up the road, there are the Slovenians, you know, who had this controversial sort of paper relatively recently, which actually sort of put forward an argument that MBL may not exist in the thermodynamic limit due to a scaling of the Paulus time, which was extracted from the analysis of the spectral form factor. I mean, I just wondered, you know, if you'd be willing to give your take on that, actually.
Sure. This is being recorded, right? So
we can postpone it until after the recording if you want to.
Okay, so I have two takes on that. I think it is an interesting argument, but I don't find it particularly compelling. I have a very sort of pragmatic numeric take on that. My pragmatic numeric take on that is the following. For my recollection of that paper, I should say as a start, I have not studied the paper super carefully. So that said, for my recollection of the paper, that paper seems to suggest that really sort of the numerics that were done on kind of 10 and 20 sites is a little bit too small. But really, if you could get out to sort of the 50 to 100 site size, that would be much more convincing. Okay, but in fact, we have gotten out to those sizes. So this work that I've told you about earlier finds, not that I spoke about it in particular in this talk, but mentioned, finds using this DMRG-esque stuff, very compelling, good MBL eigenstates out at 100 sites. And so I think we actually have really good numerical evidence, actually, that even at the size 100, these MBL states in one dimension really honestly exist. And so unless someone comes back to me and says, look, really, it's not size 100 you need, it's size 20,000 you need to numerically validate it, which is something I have not heard yet. I feel that the sort of just numeric evidence, sort of ambivalent of the theory behind it, is pretty compelling. Okay, my second comment, which is much more ill-informed, and so I should take it with more, you should take it with more of a grain of salt, is my understanding is that a lot of the argument being made really is kind of extrapolating in that paper out from the ergodic phase. And I think it's very hard to look at things in the ergodic phase and sort of conclude whether or not the MBL phase can exist, because there are some second order aspects of the phase, but there are also some sort of first order aspects of the phase. And in some sense, first order things can do anything we want. And so I would be careful about that. Now, I should say that's a little bit of an ill-informed opinion, and so I would take that with a grain of salt. I think the bigger opinion is that we have good numerics out to size 100. And so if we have this discussion, someone should come to me and they should say, really, look, this is the system size you'd have to do to really convince me that MBL exists. And then maybe we can do it. I mean, 100 wasn't really the limit. They just thought that was a big enough size. And so I would be much happier having this conversation where we really talk about, if really the worry is you haven't gone to big enough system sizes, let's tell the community what system sizes we really want to be at to be convinced, and then we'll see if we can pull that off.
I guess what I find particularly interesting about the debate is that it's ultimately will be settled by the experimentalists, right? Because I mean, you would imagine that if you have a very good analog quantum simulator on an optical lattice that you can really trust, then, you know, it's something that you could really sort of test this on much larger system size than what you can simulate on a classical computer, right?
Yes and no. I mean, I think you're certainly right about that. I think as a practical matter, even today, there have been a number of cold atom experiments that have tried to prove this. There's always a lot of quibbling going on about in the cold atom experiment if you're seeing really what you think you're seeing, and if you're in the right regime, and if everything matches, and if you haven't like heated up the system artificially. So I agree. Once the analog simulations are sort of turnkey enough, I think you're right. I think we're still a little ways to sort of really pulling that off, where sort of without controversy, someone can do something and everyone will be sort of convinced.
Thanks. That's perfect. Cheers.
The final thing I should say is about this paper is that the general community consensus is that MBL and 1D really exists. So if you just want sort of proof by authority, there is this paper, and there are a lot of people who have thought about it a lot harder than I have. And the large spread consensus is that, in spite of the arguments being made in this paper, which are interesting, the general belief is that MBL likely
exists. Fair enough. I'm sort of on the fence, so I don't have a strong opinion one way or another.
Sure. I mean, this is just right. One shouldn't take proof by authority too much, but this is at least worth knowing. Okay, additional questions?
Aren't there mathematically rigorous results in one dimension on that?
Yeah, good. So
No?
There's an argument by Embry that is very, very close to mathematically rigorous.
Okay.
So certainly any physicist would say, yes, it's mathematically rigorous. There's some quibbling in sort of the very mathematical physics community about like quite exactly are all the sort of I's dotted and the T's crossed. But for this very particular model, there is something that is essentially mathematically rigorous.
Okay, I think Tom disagrees.
Yeah, my only comment is that he has to make some fairly strong assumptions about energy level repulsion, or so this of course is far from being established mathematically, but looks reasonable at a physical level, perhaps.
Okay, fair enough. So there's a mathematical-esque argument, and whether it's certainly not formally completely rigorous, and so then the question is whether everything really pushes through.
Other questions? We'll stop the recording then. Let's thank Bryan again, and I'll stop the recording and we can continue less formally. Okay.
Great.
Thank you very much.
So what do you really think now, Bryan?